He's like, defines phi given little phi, right?
That's
Something like that. It's kind of,
it seems like defining big phi and then like little phi in terms of that, and then making sure that that's true is like more meaningful. But that's just me.
say again? Say defining big phi.
So you define big phi and then little phi, kind of like we defined a little ad in terms of big ad, and then you prove the relationship between them, and then it almost seems to mean more. But
Oh, I don't know if I'm disagreeing with you. He says that this defines the capital phi implicitly.
I mean, yeah.
Oh, okay. But I mean, the thing about that is whenever you write, it's very. The question that's bagged is how do you know everything in G, right? Because phi is allegedly going to be group homomorphism from G to H for some H, right? And the question is, how do you know everything in G can be written as the exponential of something in Lie algebra, right? That's very presumptuous. That's not in fact true. For certain Lie groups, you can't write, not everything is the image of something in the Lie algebra, right? The exponential of the Lie algebra is not onto the Lie group in all cases. So that's definitely something that has to be kind of dealt with in this thought process. The other thing is injectivity, right? We don't have, how to say this? It doesn't have to be one-to-one either, right? The exponential, so there's something there. All right, so. But I want to show you this calculation. It's really crisp and clean. It's like, okay, so but what you can do, right? And this is the point. The Baker-Campbell-Hausdorff relation is the following, at least written in terms of logarithms of exponentials. It says log of e to the x, e to the y, is equal to x plus y plus 1/2 x with y plus 1/12 x with y minus 1/12 y bracket xy and then stuff, higher nested brackets. Oh, come on. Ah!
Oh, you're gonna get another one.
No, I'm just coughing. I thought it was going to cough and then resolve itself, but it's not. Where was I? Yes. Okay, so we want to think about x and this is only true if x and y are sufficiently small. Okay, so
It's not supposed to be evident at the moment with the dots over it.
yeah, they're brackets of 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 brackets.
With like coefficients.
Exactly. Yeah, I was asked that in linear too. I said I don't know. It's not something I know. In fact, I don't even know this minus sign, honestly. I was right, plus or minus 12.
Well, I guess because they switched the x and the y in the second bracket. You just want it to be YYX.
We can work it out. We'll work it out here in just a minute or two, okay? All right, so what happens if you look at like phi? What is phi of log of e to the x, e to the y? I mean, these are the algebra elements. This is a Lie algebra homomorphism. So it's linear algebra and it's linear and it preserves the bracket, right? So basically, you got phi of x plus phi of y plus 1/2 phi of x, phi of y plus 1/12 phi of x, comma phi of y, and the other 1/12 term, which I'm not writing. All right, the point is, because phi is a Lie algebra homomorphism, preserves the structure of the brackets, right? But then we can use Baker-Campbell-Hausdorff one more time, because by the way, it's also, it's a Lie algebra homomorphism is after all a linear transformation, which is continuous, which means something small stays small, right? So it's still small. The images phi x and phi y are also small because x and y are small. And so this we can also write as what? This is log of what? E to the phi of x, right? E to the phi of y. Using Baker-Campbell-Hausdorff with x replaced with phi x and y replaced with phi of y. But then what? He says, well, what else do you know? You know e to the x, right? E to the y is equal to e to the log of e to the x, e to the y. This is... Okay. So what's that tell us?
E to the phi.
Let's say, let me start us out on the right foot here. Phi of e to the x, e to the y is equal to what? So it's equal to e to the log.
Right. It's phi of e to the log of that, which is going to be e to the little phi.
All right. So first of all, you're sort of thinking of all of this as all of that, right?
Yes.
But that, well, that this is equal to that, but then this should be equal to what you just said, e to the phi of log of e to the x, e to the y.
Yeah, which is e to the log of phi to the x, e to the... Yeah.
Which is, of course,
E to the phi of x, e to the phi of y.
which of course is what?
Phi e to the x times phi e to the y.
Right. Again, using our implicit definition of the group homomorphism, this is big phi of e to the x, big phi of e to the y. Let me try to explain in words what we've just shown.
Well, in the top line, where does that log come from? When you go from big phi to little phi.
Well, this here,
No, the one line below that. Yeah, where does that log come
it's because this is equal to that.
from? So shouldn't it be e to the log of that?
But it's big phi of that.
Right, which then goes to e to the little phi of that.
Right. Sorry, I missed one step. I guess you could. Yeah. Okay. Fine. Fair enough. I could write one more step, which is it's big phi, right? I guess the step that would, if I put this in, it would be less confusing, right? If I put in this step also, then it'd be super clear, right? This is what's keeping you from seeing it, right? I haven't written that yet. Yeah. Yeah. So let me put in the words what we've just shown. What we've shown is that if we define, setting aside the worries about onto and injectivity of the matrix of the exponential mapping, all right? If it does make sense, as it should for small x at least, well then for small enough x, then we can show that that the group homomorphism defined in this way, all right? Well, that's the thing, it actually is a group homomorphism, and the structure of the group homomorphism is coming from where?
The structure of the Lie algebra homomorphism.
Exactly, it's coming from the fact that we had a Lie algebra homomorphism up here, right? Connecting H and G, I suppose. And moreover, here you're looking at like e to the phi of stuff. So this is like an exponential of an h element. This is like e to the frac h that we're thinking of as being the big H also. I mean, so it all makes sense. I mean, this is something in another Lie group that is that's formed by the exponential of the frac h. And the Baker-Campbell-Hausdorff relation, what it shows is that knowledge of the Lie brackets, right? Knowledge of the Lie brackets of the Lie algebra here completely govern the group multiplication, at least for small elements. Well, for things that are exponentiated from small elements. In other words, as we kind of understand from our previous work, it's for stuff close enough to the identity. This pins down the multiplication. Let me show you how this works out. Let me just, in gory detail, let's just work out the Baker-Campbell-Hausdorff relation. I'm not going to be too greedy. I'll just do it. I'll derive for you guys the 1/2 term. That's all I can do. I mean, I have worked out by hand the 12th terms also, but I also know that will take us an hour. But the half we can get pretty fast. All right, let's see if we can do it. Go for it. Because doing this will also help us appreciate why it is we want to invest the time to understand the more theoretical way of doing it, right? Now I think the next, I might just keep going, I may just do the Heisenberg example next time we meet. I don't know if we're actually going to get to the full bore Baker-Campbell-Hausdorff yet. His Heisenberg example might be really interesting and worth going over. I'm not sure. I don't mind just going over examples with you guys now that we've hit the meat of the course. I think going over examples is appropriate. Where was I? So what I want to show is that e to the a, e to the b is equal to e to the a plus b plus 1/2 a commutator b plus dot 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 dot. Now the dot 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 stuff, think about it. It's like 3rd order, or 4th order, or 5th order, or 6th order in A and B. If you think about the collective order. So all I have to do is show that these two expressions are equal up to 2nd order in A and B. So I've got 1 plus A plus 1/2 a squared plus stuff I don't care about. 1 plus b plus 1/2 b squared plus stuff I don't care about. And that's equal to 1 plus a plus b plus what?
AB.
1/2, well, 1/2 a squared plus, what'd you say?
AB.
AB
Plus 1/2 B squared.
plus 1/2 b squared. Okay, very good. And then on the other hand, we have e to the a plus b plus 1/2. I'll do a meet in the middle proof. I think that's the fastest way to do this one. So we got what we got. Oh, first of all, that's actually the exponential. Let me write it out a little more explicitly. A plus b plus 1/2 ab minus 1/2 ba. All right. Oh, and there's plus dot dot dot. Fair enough.
So now just definition of the exponential.
Right, and then, oh yeah, then the definition of exponential, which is identity plus everything in it, right? That's the, if I think of this thing as being u for a second here, right? This is all just the u, okay? What's the next thing? 1/2 u squared, right? So 1/2, this stuff squared, well, this is 1/2 u squared and u squared, right? But be smart. You don't have to write down everything. You just have to write down the stuff that could possibly lead to second order. So you got like a plus b. Even the AB term produces at least cubic terms when you square that. That's it. I mean, the third order piece has third order data because there's no constant. So you got I plus A plus B plus 1/2 AB minus 1/2 BA. And then that guy gives me what? So you got yourself an A squared plus AB plus BA plus B squared. Oh, and then stuff we don't care about. There it is. That's it, all of it up to quadratic order. And then you just gotta like, you know, cancel some stuff. So for example, this guy and that guy meet an untimely fate. This one, on the other hand, reinforces that one, right? And there you have it. I plus A plus B plus 1/2 A squared plus AB plus 1/2 B squared. And that is exactly the quadratic order e to the A times e to the B. The second order. This is the relation. I have assigned this in various courses before. It's not too bad. To derive the 1/12 terms is not too much more. It's just not something I want to show you. But if you adopt this meet in the middle approach, it's pretty straightforward. Now, that leaves you. That's a really like worthless proof.
Yeah.
It doesn't give you any idea where the half came from. It gives you no sense of what the next thing is. Hardly. I mean, you kind of get some kind of. I mean, maybe you can start to see something if you. Maybe if I just spent a week calculating these out to like the 7th order term, I would gain an intuition for how the coefficients are accruing. That's probably true.
Can you make a formula for it, or no?
There is some way to just derive these pretty fast, like, because I remember I mentioned to Professor Bakalov at State something along the lines of, I don't really understand. I mean, there's a Baker-Hausdorff relations, but that's just kind of mysterious. I said something along those lines to him, and almost, I mean, as if it was an insult for that to say that was complicated, he just like started just like this. I mean, so there is a way to understand it and just to be able to derive things. Maybe we'll discover that. Maybe that's also, I mean, there's
It's 5 o'clock.
there's usually a way to derive it like sort of informally. If you set aside worries about convergence and rigor and just are looking for some sort of method to derive things, there's usually a faster way. I personally don't know that way yet. Like, I don't know. I can't tell you personally. I don't know offhand what's the next coefficient flat past the 12th. Right. And yet I know that these allow you, like, for example, an application to this in physics. momentum commutes. So like P1 and P2 is equal to 0. So if I have e to the P1 times T times e to the S times P2, then this gives me e to the TP1 plus SP2. Like that. Plus what? Plus something that's 0.
Oh, because they're all, yeah.
And there's a way of making a correspondence, like you can do this e to the, so let me just say it, so like e to the TP naught plus XP1 plus YP2 plus ZP3. Oh, tell you what, forget about the time. Let's not be weird. There's a correspondence between this and the point XYZ. So you can use the exponential of the momentum algebra to represent physical space. And in this approach, in this way of thinking, multiplication by momentum, what does it do? It takes you can think about your initial point being, let me use an x. Your initial point could be at like xp1. You multiply by yp2. You go to xp1 plus yp2. Or you could think about it this way. I have e to the x, xp1 plus yp2 plus zp3. Right? I multiply by e to the, let's say, a, here's a better notation, a dot p. And this would be like e to the r dot p. Right. What you get is e to the r plus a dot p. There's a more efficient way of writing it. In other words, you've gone from r and you're mapping to r plus a. You obtain this by multiplying by the exponential of a momentum operator. It's generated a translation. That's a translation. So the exponential of momentum gives you translation. You can likewise show that exponentials of like angular momentum generate rotations and other things. So there's this world of exponentiating representations of physical operators to generate motions on physical space, where the physical space is thought of in terms of as being represented by exponentials in a certain way. I think the way to understand this more carefully in terms of mathematics is through the study of homogeneous spaces. A homogeneous space is one that's formed from the quotient of a Lie group by another subgroup. So homogeneous spaces have the structure of a quotient group, something like G mod H. Your whole space, basically, like your space is like isomorphic or maybe diffeomorphic, I don't know, whatever, it's the same. You're modeling your physical space or your just whatever kind of space you're thinking about by a quotient of two groups. For example, if you take the group of rigid motions, what would that be? I think it's called, whatever, you would say rigid motions, let's just, for lack of for me forgetting the name of it, I think it's a fine SO3. Yeah, that's what it is. A fine SO3. This is rotations in 3 dimensions plus translations, all right? You take that, you mod by SO3. Basically, you're modding by the rotations. This is essentially just R3. But it's R3 where you get to represent points of R3 in this way as exponentials of translations. See, because ASO3, well, little ASO3, I should say, it's the span of things like, well, you've got your translations, your P1, P2, P3, and you've got your rotation generators like J12, J23, J31. I don't know, this is too much. I think I can get away with just like 2 of these or whatever, but there's a larger story to tell here in terms of like its application to physics and geometry and such. That even when you start to understand that this Baker-Campbell-Hausdorff thing, it becomes more interesting than just being a device for proving this rather interesting, mind you, but rather abstract mathematical claim. It's the bread and butter of how we actually calculate things in physics, the relation between the Lie group and the algebra, the exponentiation. Exponentiation is made possible by the Baker-Campbell-Hausdorff relation. So like it was like Sesame Street, like brought to you by the letter G. It's like modern physics brought to you by the letters B, C, and H. Sorry, much too much Sesame Street once upon a time. Well, I must run. As you know, I have parties to go to. Maybe not as glorious as the paint party we've been advertising around here lately, but